Finding the square root of a number is one of the fundamental aspects of math. Sometimes a number is a perfect square, so the square root of 25, for instance, is 5, because 5 times 5 does equal 25. But to find the square root of 2, for example, it's not 1, it's not 2, it's somewhere in between 1 and 2. There are different techniques for finding the square root of a number, and I'm going to go through one of them here. This is sometimes called the long division square root method because it resembles long division a bit. So the square root of 3,364. We start by taking the last two digits and kind of group them together, and then the next two digits and group those together. We ask ourselves, the square root of 33 is between which two numbers, and the answer is it's between 5 and 6, because 5 squared is 25. We put the 5 over here. We square it. 5 squared is 25. We subtract, just like in long division, get 8, and we bring down the next two digits. Now comes a cryptic step, which will get explained why it works afterwards. To find the next digit, we take the number, the answer so far, which is 5, we double it to get 10, and we take that 10 and say, I want to find a number so that a 10 with a number after it, in other words like 100 and something, multiplied by that same number, that same digit, needs to be as close as possible to 864. And you could try some numbers. 101 times 1 equals 101. That seems to be too small. And 102 times 2 is 204. That seems to be too small. But when you eventually get to 108 times 8, you get 864, which is exactly what I wanted. That 8 goes up here. The 108 times 8 goes down here. No remainder means the answer is 58. If the number you're trying to find the square root of has 6 digits, again we group it into groups of 2. If the number has an odd number of digits, we put a 0 in front of it so that we can have the last group of 2 also. Same thing as before. Square root of 33 is bigger than 5 but less than 6. We subtract. We bring down the next two digits. We double the 5 to get 10. We ask ourselves 100 and blank times blank is as close as possible to 898. And it turns out that 8 is the best we can do there. 108 times 8 is 864, but 109 times 9 is too big, so 8 is the next digit. We subtract, and we bring down the next pair. Now, we don't double the 8. We do 2 times 58 is 116. 58 is the number on top so far. And we ask the question, 116 blank times blank is as close as possible to 3489. And with a calculator, you could try 1161 times 1 is 1161, which is way too small. But 1163 times 3 is exactly 3489. And that's the next digit. And since there's no remainder, this big number originally was a perfect square. If you're wondering, is there some way of deciding a good number to choose, to test, rather than start it at the number 1? A little rule of thumb is if you were to divide 3489 divided by 1163, that would be pretty close to the actual. It often is the answer. That's kind of like, I guess I'm thinking 116 let's say it's almost like saying if I divide by 116, sorry. It's almost like the smallest thing. Yeah, I don't have a good explanation for the starting number right now. Oh, sorry. Let me say this better. If we divide by 3489 by 1160, that will get approximately, that'll get close to the actual answer. Now, the next question is, why does this process work? Well, let me go back and show you another idea on this. Square root of 3364. I know it's between 50 and 60, because 50 squared is 2500, and 60 squared is 3600. So I could say, to get the next digit, it's 50 plus whatever the next digit squared has to equal 3,364. Using some multiplication of polynomials from algebra, this thing will become 2500 plus 50x plus 50x plus x squared equals 3364. If you subtract 2500 from both sides, you get 864 equals 2 times 50 times x plus x squared. Notice the 2 times 50 there? That becomes 100x plus x squared is equal to 864. So to find the x, I could factor it out and say x times 100 plus x equals 864. And that's exactly what happens when, in the last step, when you were doing 100 and something times something, same sort of idea. So that gives a little bit of the mystery of why we double the 5. It has something to do with when you increase your answer from 50 to 50 whatever, the square goes up by, you end up having to double the 5 at some point in that process. Now, to find something like the square root of 2, which is an irrational number, the method is put a 0 before it, put a decimal point, and put a couple of groups of zeros. Now, just to remind you, the square root of 4 is 2, the square root of 400 is 20, and the square root of 40,000 is 200. So when you multiply something by 100, the square root gets multiplied by 10. So instead of doing the square root of 2, I'm actually going to do the square root of 2 million. This decimal point's here, and it's going to go in the answer also, but you could just think of it as, oh, we're just trying to find the square root of 2 million, at least the first digits of it. So the way we do that, square root of 2 is between 1 and 2, so I put a 1 up here. Subtract, bring down, double the 1, it becomes 2, so 20 something times something is less than or equal to 100. 24 times 4 is 96, so 4 is our next digit. Subtract, bring down. Double the 14 to get 28, so 280 something times something has to be close to 400. It ends up being 1. 282 times 2 is too big, so 281. Subtract, get 119, bring down the next two digits, that's those. Now we say 282, that's double of 141. 282 something times something has to be less than or equal to 119, or 11,900. Turns out that when you multiply 2824 by 4, you get 11,296, which I'm going to stop at this point, but we can keep going with this process and getting more and more digits. 604. If I want more digits, I just add 2 more zeros, bring down the next 2 numbers, and continue on the process. So you can use this process to do square roots of irrational numbers as well.